It was, I rewatched it myself, and yep, I said it wrong. So, lest any of you lost sleep over it. Okay, we did this, and everything I said is right. It's just at one point I said, oh, when it's in this position, it'd be a lunar eclipse, and it was actually the solar eclipse. So, I'm going to differentiate those two for clarity. I'm not testing you on this, but if the sun rays come from over here, and the moon casts a shadow onto Earth, and we're standing here on Earth, the moon is now in the way. It's blocked the light from the sun. That's called a solar eclipse. I brain farted and said, I don't know what that is. Well, that's the lunar eclipse. Duh. And yeah. See, now I'm brain farting again what I said. Anyway, I think it was wrong. I felt like it was confusing. This, we can still see the sun, but the moon disappears. So that's the lunar eclipse. Because our shadow is being cast onto the moon. However, somebody mentioned, was it you, Max? About who asked about the light rays coming in and all the sun? Some of the light rays can go around the edge here. What light gets scattered out more than the others? For visible light? When it goes through more and more atmosphere, yeah, the blue, the higher frequencies. And so that's why our sky looks blue, leaving the reds and greens to get through easier. And the more it goes through, the more it gets scattered. If a whole lot gets scattered, all that's left is red. And because it goes from space to the atmosphere, it changes mediums. The speed changes, in quotes. And so it bends, it refracts. And some of that can still land on the moon, which is why it can look blood red or orange in a lunar eclipse. Anyway, I wanted to clarify that, lest I threw somebody else off. So there. Here's an animation I found. You can think of this as the sunlight coming in. It's got all the different colors, red, green, blue. It's kind of small. There. Coming in. When it hits our atmosphere, the blues and the greens you can see are getting scattered off more all the way through it, leaving more reds and yellows, oranges to get to the person. If you were solar radiation, all of it hitting you, just fry you. Then you might freeze, then you can't breathe, and you'll explode. But you know, I think you'll die first from solar radiation. What they do is they hit something around our Earth. It's the magnetic field. Magnetic fields influence moving charges, these electrons. And it gets them to spiral around the magnetic field lines. And then when they come in to our atmosphere, they get ionized, which means they strip atoms in our atmosphere of electrons. When they recombine, they have to give up that energy that they gained, and they give it off in the form of light. That's the auroras. And that usually happens around the north and south poles, because that's where the magnetic field is the strongest. Which is why we don't see them much down here. Oh yeah, I didn't do that the other time. I didn't finish that. If the sky scatters high frequencies more than low frequencies, which it does, why isn't violet scattered more than blue, which it is? So why is the sky blue instead of violet? Great question, because it should be. The main reason it isn't is because our eyes are way less sensitive to violet than they are blue. So we detect more blue. It dominates our signal. The human vision peaks in the yellow-green region, wavelengths, which blue is closer to. So we detect all those blues that get scattered better than the violets. But the violets are smaller and do get scattered more than the blues. So if our eyes were different, the sky would be purple. All right, we had a question. Some come up in another class that some of these students are in, and I'm going to answer it because it'd be a good kind of review practice for this class. You don't have to know everything, but here's the gist. You have an eyeball. Light rays can come in. What happens when they go from air into your eyeball? They refract. Yeah, you should know. That's your superhero paper is. Because it changes mediums. It slows down, so it bends. And for a healthy human, if they form an image on your retina where your sensors are at, then we say this person's 20/20, doesn't need corrective vision, blah, blah, blah. Now, if you were to go underwater, do you see as well? No. What can help you see better underwater? Goggles. This is why. If you change the air to water, and the light rays are coming in through the water, and they go from water to your eye, do you think they bend more or less? Oh, we got both. Do you think light travels faster in air or water? Air. It's the interactions. There's less of them to slow it down in air, so it travels faster in air. So it gets slowed down in water. That's why it bends when it goes from air to essentially a big bag of water. We're approximating. So if you go from water to mostly water, it doesn't slow down as much. So there's not as much bending. And so it won't bend as much. It might form back here. And so, if we go underwater, we become, which, Stephen? Nearsighted. Nearsighted is where, no, actually farsighted. The image forms back here, underwater, which is behind our retina. We would need help. We'd need a corrective lens to help us focus it even more, to get it back over to here, underwater. When you wear goggles, what that does is essentially turn this back into air. So it goes from water, but then into air to your eyeball, which is what we're designed for. That's why wearing goggles underwater helps us see better. Because instead of going right from water to water, which doesn't work as well, doesn't bend as much, makes us farsighted, we put a layer of air right in front of our eyes. Yeah, Casey?
If you're a nearsighted person and then you went swimming with no goggles, if you get closer to the
Yes. Yeah, actually, I'm nearsighted. So that means naturally, my eye is focusing too strongly. It makes the image up here. That's nearsightedness, in front of the retina. So I'm already up here. So if I go underwater where it doesn't bend as much, yeah, it'll move that back. So I actually could see better a little. I have an astigmatism too, so it doesn't help a lot. You're just a big blur. So. So the reverse is true for the fish. If you took a fish which was designed to do water into its eyeball, and if it can see normally, and now you bring it out of the water into air, it's going to bend even more. And the image will now form in front of the retina, and you just made the fish nearsighted. So a fish out of water is nearsighted. But it all has to do with the speed of light, changing mediums, and bending stuff. Kind of fun. So I think you guys had it, it moved it right. Got it mixed. It can get confusing. But if you're nearsighted or farsighted, you know how light is bending in your eyeball. So again, for me, I'm nearsighted. So my eye is either too long or too strong, or both. It's bending it too quickly. This is why you guys are out of focus. So I use some corrective lenses that spread it out first. It makes these actually spread out a little first. So that then when they bend, it takes longer. And now I can see. And farsighted is the reverse. Contact's the same thing. They're just made to be right on your eye.
So when you get laser surgery, they're planning reshaping?
Very good. Laser surgery, they're essentially reshaping your cornea, that curvature, to correct how much the light is bent or refracted so that now it lands on your retina. Yeah, because if you're bent too much, you're this case. Well, let's flatten it out. Now I can, and vice versa. After his surgery, they put a drop on his cornea to make it flexible again? Was it to make it flexible or just to keep it moist, to heal? A blue dot. So it can, I don't know about that. I should reserve my comments. I don't know. It's fun though. You can YouTube some of the videos for laser surgery. They actually cut some of the cornea, whoosh, flap it back over, zzz, put it back on, then try to keep it moist. My dad actually did the radial keratotomy where they did the same thing but with a knife instead of a laser. And it worked just fine. But you know how when you see floaties in your eye, like you're looking at the sky or bright lights and you see those little things moving around? They're just inside your eye or on your cornea casting shadows onto your retina because they're too close. You can't focus on them. So they're essentially casting shadows like we did. And you can see blood vessels and tissue floating around in your vitreous humor. Anyway, he could see the scars, the 7 radial scars he could see when he would do that. Anyway, but it corrected his vision because it changed how much it got bent or refracted. I'm going to save that. Let's do some color again. Review that. Because if this is the first time you ever thought of this color stuff, you'll have to go and study or get on your cheat sheet or review some of these mixings of colors. So red, green, and blue. And we need it darker. Let's just go for that. I wanted to do some colors here. So this red I think is a little strong, so I'm going to back it off. All right. What color do you think this is? A navy blue, purplish. Yeah, it's kind of, but it looks really kind of dark. Yeah. Let's put it over here in the blue. Looks mostly, doesn't seem to change much. It's just a little darker because there's not as much light shining on it. This gets 3 times as much light. Let's move it to the yellow. It gets a lot darker, doesn't it? The pigment in this, if it's blue, and you shine blue light on it, then the blue light reflects off of it and it looks like what you thought. White light has blue in it. So the blue light reflects off and you see it as blue. What 2 colors are getting absorbed mostly? This isn't a pure blue. Red and green. What make up yellow? Red and green. So if you only shine red and green on it, there's no blue to reflect off. So it looks dark. Nearly black. Does that make sense? The subtracting color. Let's try a different one. This is sort of red. Looks red. kind of reddish orange in my mind, but well, let's see. So if we go to red and green here, that still has red in it. It doesn't change much. Red shouldn't change much either. But let's see green. Whoa. Or add some blue into it. Yeah, this pigment absorbs blue and green mostly. That's why if you only shine blue and green on it, it looks dark. But now we got some red. Now it's only red. We can see it because the red can reflect off. Which colors resonate with these pigments? Good. It's the green and blue. That's why they get absorbed and heat up this cloth. Red reflects. You want one more? Let's try yellow. So it shouldn't look much different. Whoa. Because this is reflecting red and green, absorbing blue. So if we only shine red on it, well, it can only reflect red. So it looks a lot more red. There's a little orange in there, right? If you only shine green on it, well, now it looks green. Shine both, you get yellow. It absorbs blue, so let's go over to blue. Yeah, now it looks dark. At least the gray. Again, it's not a pure yellow. That's kind of fun. So, clouds. What color are clouds usually? White. So you know immediately what wavelengths are coming back to your eye from the cloud. All of them. Red, green, and blue. But clouds are made up of different sized particles. It's made up of raindrops. You might not have known. I like writing this down. If you have tiny droplets, really small water droplets that start forming in a cloud, I bet you can already guess. They're small, little mass, little inertia. What frequencies do you think they naturally like to resonate at? High ones or low ones? We got a high and a low. So let me break the tie. Another high. Now I'll help. If you had different bells, different shaped or sized bells, little bells, big bells, compare their frequencies to their sizes. You had a little bell, what will it sound like? Ding, 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 ding. You take a big bell, bong, low frequencies. It works that way with waves, with particles. Something that's small can vibrate faster. So the tiny water droplets tend to scatter blue light from the sun. So if you ever tend to notice a bluish cloud, which is rare, you know it's made up of a bunch of small water droplets. Medium and large. What do you think large does? It's going to scatter the reds, because they're like the bigger bell with the longer wavelengths that vibrate more slowly. And, greens will be in here. Since the clouds usually look white, it's made up of all kinds of different sizes of water droplets, because it's white. It's scattering, the small ones scatter the blue, the medium the green, and the big the reds. They all scatter and combine in our eye, and they look white. By the way, what if you had some even larger, huge droplets? Bet some of you can reason this through. Small ones do blue, medium green, large red. What if we got even bigger? Infrared. They would. Those start scattering some infrared. They start absorbing the visible because they're big. And if you get humongous, I always spell it wrong. Humongous. You get rain. They're too heavy. Gravity can't, and the air drafts can't keep it up. Balance of forces again. Get bigger and bigger and bigger. It's weighing more. The updrafts can't hold it up, and it'll come out as rain if they get too big. But before that, we see the cloud. It's just a big puffy thing of different sized water droplets. So this paraffin wax is kind of like a cloud because it's made up of paraffin wax, but they're all different sizes, kind of like this. And you wouldn't even have to know that anymore. You see something, if this looks white and you know it's made up of a bunch of stuff, they must be different sizes. Because this is scattering light off, even if you shine a light on it. You can kind of see here, let's dim it a little. So the light goes in, and it still looks white. Remember when I did it with that rock and the egg? The scattered looked more blue, at least more than this. This, it still definitely looks more white. So what's scattering it must be a bunch of different sized particles. It's white, so every color must be getting scattered. Water. What color is water? Trick question, huh? It's clear, you dummy. Yeah, but when we look at the ocean or seas or things, it tends to be more blue or sometimes even green. That's the color that's making it to our eye. So what color tends to go away? Yeah, red. If you take white and subtract red. So water must be absorbing the red. Well, large droplets, water droplets, yeah, they absorb a lot of red and infrared. How many go scuba diving? Anybody? Oh, our operator. What color do things look like down there? Dark. They definitely look dark because a lot of the light's getting absorbed or dissipated or scattered out the deeper and deeper you go. But they can look some color. Like, have you ever done the coral reefs or seen pictures? Actually, the pictures, they edit those. Or they use filters to see the colors more naturally. In person, they're going to look more red. Because that's what's getting through. The blues and the greens are reflecting, getting scattered. That's what we see. So they have to put filters in and adjust those to see the real colors. It would warm up the water. Anytime a color gets absorbed by anything, even like these, if it's getting absorbed because it resonates with those pigments, that energy has to go somewhere, and it goes into heating it up. So yeah, you absorb, if water absorbs any wavelength, that's going to transfer the energy to the water and it'll warm up. That's what happens in a microwave, by the way. The water molecules, not the electrons of water, resonate at microwave frequencies. Here's a water molecule. If I'm oxygen, and here's the two hydrogens. You know, it can move around all on its own. That's how hot it is. This is a measure of its translational kinetic energy moving. But the water molecule can also vibrate. It can vibrate like this. 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 And those frequencies that it naturally wants to vibrate at match microwave frequencies. So if you hit it with microwaves, it absorbs them. That's why things that have a lot of water content get hotter faster, because it starts going like this. They start moving. You can think of it as microscopic friction. They start bumping into their neighbors and transferring that energy to them, and they start moving, and eventually your whole food gets hot after it conducts through it. Things that don't have water, that don't resonate with microwave frequencies, like metal, don't get hot because they don't absorb the waves. Metal will just reflect them, and they'll bounce around inside your microwave going nowhere, just building up. The danger is some of those could go backwards into where they're being emitted and damage the source. That's why they say don't to put metal in a microwave, because it doesn't absorb the waves. They won't go anywhere. They just build up. So that's clouds, water. Eyes. Who has blue eyes? That works from scattering. It's like the sky. Your eyes are like the sky. Light goes in and the blue gets scattered. It tells you something about the size of the pigments and particles in blue eyes. Who has brown eyes? Should be more. It's dominant, right? Dominant trait. That's the pigment that absorbs. It likes to absorb blues. I don't know if you remember, red and green made yellow, but if I change the intensity, if I decrease the intensity of red and green, it got orange and brown. So it's absorbing some red and green, but not all. But it's absorbing blue. That's why your eyes look brown. Yeah?
So I have a brown dot in my blue eye. So would that be kind of like
I want to see. Do you mind?
okay. In this eye there's a
Cool.
brown dot. So does that mean that part of my eye is absorbing my blueness?
Yeah, that would be a very logical, and I'm going to go with that theory explanation until we know otherwise. So here's our eye, here's the pupil that's dark. It's about, roughly to scale, about like that. There's a brown dot. That could totally explain it. Maybe the pigment is just different right there. And if so, that would totally explain it. Could be there could be another explanation, I don't know. But that could easily explain it and happen. Nobody's asked, who has green eyes? That's a mixture. You got both going on. Some pigment absorbing blue, but also the other pigment scattering blue. All right. We're fully into chapter 28. We've already covered half of the stuff. I'm not asking any homework questions on 28, but it relates. Basically, it does geometrical optics with reflection and refraction, which we've already been discussing. I'm just not going to hold you to things like mirrors and lenses. But it'd be very beneficial to read if you feel like it discusses principle of least time. Remember how things, when they refract, you can consider the path they take, how much they bend. It gets there in the least amount of time possible. That's the lifeguard running on the sand versus the water. Straight isn't as fast because the speed's different in the two mediums. The law of reflection we already discussed. You already know what refraction is. Basically, mirrors and lenses just use all that to form images. Just like this. Here's a curved space and there's a lens in there. And based on that shape, it changes mediums, it refracts. And if you have multiple rays coming in, they can form a focal point. So you can get an image. That's mostly what I'd like you to know out of 28, so you don't have to stress too much on that. But there are two things I thought are cool. One, mirages. Do you remember I showed you the video of our author? And he had two camps. You know, some tents over here and some tents over here, and they're talking. Hey, how you doing? Fine. And that was sound waves. They bent, refracted, because of the difference in temperatures. Travels at different speeds, so it bent. Light does the same thing. Who's seen a mirage? No. Who has never seen a mirage? Okay, I find that hard to believe. Maybe you didn't realize it. Who's ever seen, it looked like you've seen water on the highway out in front of you? Have you seen that? Those of you that thought you never saw a mirage? You know what? I got a picture. There's one. Anybody? The picture I drew, and it works the same. Say you're in the hot, hot desert. You know, you got your palm tree over here. And the sand is really, really warm down here, but the air above it is relatively colder. And if you're standing over here, whoops, there's your eyeball. Yeah, you see the tree because these light rays can get to you. They go through the cold, nothing happens. But if a light ray is headed down in that direction, it's like it just changed mediums. Cold, hot. Which one does it travel faster in? You're right. This is the one that always confuses me because they're the same for sound and air or light. That's because it's a different reason, but they're both for interactions. So sound goes faster in hot air, so does light. Sound does because it needs those interactions, the medium. This is a review. Plus, I'm just humoring myself, talking myself through it. The molecules are moving faster, so the interaction is transmitted more quickly. That's why sound travels faster in hot air. Light doesn't need the interactions. They get in the way. Well, hot air, because they're moving around faster, are farther apart. So it's less dense. There's less it has to interact with. It's not the fact that they're moving that transmits the interactions. It's just the fact that they're there in the way, absorbing the light, bloop, and re-emitting it. And there's less of it. So it goes faster in hot air too. So it's relatively slow here. Takes less time to get through. Or more time to get through, more time. And down here it would take less time. So think of that wavefront. This part will be going faster than that part, right? So it'll get ahead. And see, it bends. It redirects, and it's turning upward. So this will bend a little like this. And then it goes from an even hotter spot, from warm to even warmer. And so it bends again, and again, and again. Each time it gets in there. Redirects into your eye. And where does your brain think you saw it? Well, you think the ray came from down here. Even maybe down here. And you see a mirage. The water on the ground, which is a reflection of the sky. Reflection. It's the light from the sky coming and being redirected up. The top of the car, down to the warmer air in the pavement, gets refracted back up. That's a mirage.
So the light, so it's refracting off of
The change in the air. Yeah. Yeah, this ray, in a sense, never gets to the surface to bounce off. It's being bent. Each time it gets progressively warmer, it gets refracted a little bit more and more and more and more, and redirected up.
I think maybe I got confused where I thought it was bouncing off of like another object.
Yeah.
It's just refracting through warmer air, and then it creates the illusion.
Yeah, it's just refracting off the warmer air and creates the illusion that you see. Oh, look. Ah. Or like in the case of this picture, it looks wet. Where are we at? Rainbows. Let's do rainbows. You got to have rainbows. You have enough information to know how a rainbow works now. It's just reflection and refraction happening at the same time. So I'll attempt to draw it. All right, here's a water drop. The pictures of this are much better in your book or online, but you got sunlight coming in. It has all colors, so we'll call it white. When it gets to here, what happens? Yeah, it refracts. You know, you draw a normal, it needs to be perpendicular to the surface. So some of it reflects, but not as much. Some of it refracts. Let's see, it's going fast in air. It's going to get slowed down by the more dense interactions in the water. So it actually, instead of going, I should have drew this bigger. It's going to, it's a problem. Trying to approximate, so you just get the idea versus drawing it accurate, and it throws me off. All right, let's see. I'll try a little better. Let's do, then it's more obvious. The perpendicular. I want to do this at least a couple times. So straight would be headed that way. Well, it gets bent. It slows down, those waves bend, and it ends up going this way. Some of it will reflect. So reflect, refract. It bends towards the normal. I mean, this is called the normal. Perpendicular. So there's a little bending there. Because red and blue, violet, green, all that travel at have different frequencies, they interact at different rates and get slowed down more or less. The more interactions there are, blue, violet, the more it gets slowed down. We saw that with the prism. And what color got refracted more in visible light? Do you remember? That's right. White light went over here. And then we saw red, green, and blue. And them overlap with all the other colors. So yeah, blue ended up getting affected, bent more. So dispersion starts happening immediately, like right there. So this is the red and this is the blue. Or violet if you prefer. Then they reflect again. Same idea. You can draw the normals and do that. Some of it refracts and goes out. If you do the angles, they end up switching sides. And then some reflect again and some refract. And they come out. So we have, red here, blue here. And we're down here with the sun at our back. You never see a rainbow unless the sun's at your back. Look in there, and you need some water droplets over there. And what do you see? Oh, blue and red light get separated because it refracted, reflected, and refracted, and it dispersed, and they come into your eyes. And where do you think you see it? Well, this light came from this direction. This light came from this direction. So you see a rainbow, you know. Blue's always on the bottom of a primary rainbow. That's one of my pet peeves. I look for that in movies. I think Little Mermaid got it wrong. Red will not be on the bottom because of the law of reflection and refraction and Snell's law. For a primary rainbow, blue's on the bottom, violet. But anyway. And so My Little Pony, they just mix them all up or something. But that's okay. Now, you might be asking a secondary rainbow. A similar idea goes on. And I'll whiz through that one. There, some of the light comes down at the bottom, and it ends up doing a refraction, reflection, another reflection, and another refraction. And the reds and blues split up in here. And now you'll get it. You'll see a secondary bow at a different angle above. And these colors, because of that extra reflection, switch. So on a secondary rainbow, the blue's on the top. But it's all because of refraction and reflection in a water droplet. And what's neat, nobody sees the same rainbow. If I'm right here, all the water droplets, this, really, these are going to spread out. Mainly, I get red from one water droplet. That goes into my eye. The blue came from a water droplet that was below it. So it's a bunch of water droplets that send all this light to you. And if I move over here, it's completely different water droplets that are sending light to me now because of the angles. So when you're standing next to a friend looking at a rainbow, they're all coming from different water droplets. I better do this one. I've had it out a few times. So I'm going to put a ping pong ball up to this tuning fork. This one, we did beats with them before. Actually, where are we at? So they're not the same frequency. So I'm going to adjust the mass of this one. Thus it'll change its natural resonant frequency. Force it to drive. I'm going to drive it. It's slower now, the beat. So I'm closer. Must be this line. Let's see if they're the same frequency now. Ooh, close enough. Now I ought to be able to drive this one. If I make this one resonate, it sends sound waves out. Those sound waves could go in here and force it to start vibrating. Because it wants to vibrate at that frequency. I can force it to resonate. So that's kind of how this transfer of waves happen. Here it is with sound, but the same thing is happening with light when it travels through whatever medium. It makes something vibrates, takes the energy, re-emits the wave, gets over to here, it's absorbed because it resonates at it. It starts vibrating, sends out waves. So you can think of light traveling that way if you want. Let's put it back off resonance. Well, you know it's going to be a beat pattern now, right? Nothing. Because that one doesn't want to resonate, vibrate at this frequency. So they're not in resonance. So that might be a reflection. Or if it's transparent, it would just go through it. Much easier. It doesn't get absorbed and increase the energy. But get back onto resonance. Sure enough, it absorbs it and starts vibrating a lot more. Okay, I'm going to end with diffraction. It's a new term. I should write it. Because some non-English speakers. So we have refraction, the bending of light. Now we're going to talk about diffraction. And I'll end with it. We'll continue next time. They're both the bending of light, but for different reasons. This is, you better know by now, it's when it changes mediums because it changes speed. Sound or light, any type of wave. Any type of wave can also diffract, diffraction. But that doesn't change mediums. It stays in the same medium. It just goes past something, like an edge or an opening, an obstacle. And I'm going to show you that to end with. So here's a water tank I can make ripples in. We'll start with water waves. Let's see. So I got a little rod here. And if I roll it, I displace the water, and you can see the wave travel down. There's a pulse. Boom. And then you see reflections. It's like echoes. They bounce around. You can see the wave fronts. Think of them as the crests, the bumps. And you can see how frequently I do it. If I keep doing it, There go the wave fronts traveling down to the bottom. You can reflect them off things. Let's put this, oh, I don't know. How about here-ish? Which way should you see the reflection go? Well, let's see. The wave fronts are coming this way. The normal is perpendicular, so the angle it comes in at should be the angle it goes out at. So they should come in, and you ought to see some wave fronts going this way. Let's see. Maybe the change focus will help a little. It's not as there we go. Focus on the ripples instead of the. Now you can see some wave fronts going to the right after it. It keeps moving on me. Can you see that? All right. Watch this one. You can do refraction. Here's a piece of glass that's not as deep, it's not as thick as the water. So it can come over here. Some can go over the top, but it's shallower. So it's like it's going through thick water and then thin water. Water waves do this. This is how you get surfing waves. And you can see it bend or refract. Maybe it'd be easier to see over here. Yeah, I see it. So the idea is the wave front's coming in over here. The one that goes above this surface, it's shallower, and instead of going this way, I start seeing it go this way a little bit. Look for that. You see that bending? Because it's slowed down over there in the shallower water. Now, since we had this, I wanted to show you those. Diffraction. Here's an edge right there. We're going to send the wave past it. Watch what happens. Do you see it diffract or bend around the edge? Instead of just coming like this, some of the waves actually start curving and come off this way. Let's do it again. Now that you know what to look for. We'll move this over, give you more room. That's diffraction, the bending of waves around an edge. If you have an opening, I'll be done in 1 minute. They go, and look, they come out spherical like that. They spread out. That's diffraction. One more. 2 holes. This one will diffract, and that one will diffract. They'll both spread out. And look, they interfere with each other. Do you remember that pattern from our overhead transparencies? And so down there, they can be constructive or destructive interference. But diffraction is the spreading out of waves around an edge or through an opening. Water does it, sound does it. I'll show you with light next time. Thanks.